In this video, we're going to discuss two variations of the K-nearest neighbor algorithm, and these include the condensed nearest neighbor and the weighted distance KNN. If you would like to find more details about the original version of K-nearest neighbor, please watch the previous videos. So the condensed nearest neighbor, what it does is that it tries to find a reduced set of training data that is actually representative of the training set, but can be used in order to save computational time when deciding the nearest neighbors. So why we're doing that is because KNN is computationally expensive, and the more training data we have, the more the computational cost increases, because we need to compare every training sample with our test sample. So the idea behind the condensed nearest neighbor is that if we find a condensed set of samples that is still representative of the structure of our training set, then this will be good enough in order to take an approximate set of decisions. So how are we going to find a condensed set of samples? We use this pseudocode, and we actually use a combination of randomized procedures and some logistics that go into this. So we first randomly initialize our training set with a subsample from our training data dtrain. Once we do that, then we look at the samples of our training set in random order. So for each training sample that we look, we then find the closest training sample, X prime, which is closest to X. Now, if these two samples have the same class, then it would mean that this specific space would be pretty good represented only by sample X. Therefore, we do not need to add sample X prime into our condensed training set. However, if these two samples actually have different classes, then this would mean that there is more into that specific space that in which samples X and X prime belong to. Therefore, we would need to include both X and X prime in order to represent both classes that are in that area of our d-dimensional space. Once we do that for a random training sample X, then we repeat that for a certain type of predefined random training samples. And the idea behind that is that if we randomize the selection of samples, then we are pretty likely to get a representative condensed set that might work well enough. We do that either for a predefined number of iterations or for another type of predefined metric until our Z potentially does not change, for example, or until our subset Z has minimal changes. After we do that, then we take our subset Z, which is a subset of our original training set, and we use that subset in order to conduct our decision-making with KNN. Now, another modified version of KNN is the distance weighting KNN. So what we have seen so far is that KNN assumes that similar instances contribute in the same manner to the final voting process. So if we have K neighbors to a test sample, each of these neighbors has a vote, and this vote contributes the same to the final decision for that test sample. However, that might not always be good enough, or sometimes we might have ties for a test sample that we might want to break. This is where the distance-based KNN comes in. So for that algorithm, instead of having the same, instead of each sample contributing the same into the final decision, each sample's vote is being weighted by a weight W. And this weight W essentially depends on the distance between our test sample and the corresponding training sample. This is an example of how this weight can be formed. And in this case, this weight is proportional to the distance between sample X and the K nearest neighbor, while this distance has been divided by the total number of distances for all the nearest neighbors for the sake of normalizing this voting procedure. Now, this exponential is also being added into this formula in order to make distances more equivalent to many other different metrics. So once we compute this vote, this weighted vote, what we can do is that for each class we can find again which is the class that has the maximum number of votes, but in this case, these votes will not be an integer number, but they will be a continuous number. Therefore, it's less likely to have ties. And also in this way, it's less likely to have, it's probably more likely to have a more accurate decision-making process, just because each training sample contributes in a proportional manner to the distance, to its distance from the testing sample. So with that, this is the end of our videos for KNearest Neighbor.